In the last lecture, we introduced Gauss's law. Gauss's law was a way to relate electric charges to electric flux lines. Electric charges were seen as sources for positive charges or as sinks for negative charges, which is to say that electric flux lines either emerge from or converge into electric charges that are either positive or negative. In this lecture video, we're going to be recasting Gauss's law in a more convenient and more applicable form, a differential form. And in order to do that, we're going to introduce something called divergence. This is divided into three parts. Part one, I will talk about divergence. In part two, I'll talk about Gauss's law. And in part three, we will talk about how numerically you could solve Gauss's law for more general situations. All right, so let's start by introducing what is meant by divergence. All right, now we have talked a lot about vectors, how we add and subtract them, how we can multiply them, cross products and dot products. But we also need to cover how we take derivatives of vectors in particular. And so for that, there's actually going to be a few different ways to do it, not just one. And the primary operator that we're going to use to define these vector derivatives is called the del or the grad operator. You'll see it both ways. I tend to prefer del, but you may see it as grad as well. It's basically an upside down delta or a triangle pointing downwards. Sometimes you'll see it with a bar over the top of it since it's technically a vector, but I will generally leave that out. But the definition of this del operator is the derivative with respect to x in the x direction plus the derivative with respect to y in the y direction plus the derivative with respect to z in the z direction. All right. Now, if you look at this, this doesn't make any sense. You're taking the derivative with respect to x of nothing, and it's pointed in the x direction. So yeah, this does not make any sense on its own, and that's fine. But you could say the same thing about a plus sign, right? A plus sign, what does a plus sign mean? A plus sign is meaningless until you put things on either side of it, right? You say 5 plus 3, and now we know what that means, that you're adding these two things up, and then we of course say that equals 8, right? So the plus sign is what we might call an operator that requires something else with it. And this del is also a mathematical operator. It has to be, we have to attach it to something in order for it to do anything useful for us. So examples is going to be, we can take this del operator and we can multiply it by a scalar field v, right? So v is a scalar. It could be something like temperature or pressure or cost. Any of those would be a scalar field since there's no direction associated with that. And if we do that, this is going to be something called gradients. And gradient is a vector. We'll cover that later. You could also take this del operator and take the dot product of that with a vector field, right? So a vector field A, this could be something like wind, right? Wind, which has intensity and a direction associated with it. And so we can take this del operator and take the dot product. If we do that, that's going to be something called divergence. That will result in a scalar since a dot product gives us a scalar. And that's what we're going to talk about today. Let me just talk about a few more. There's also, you can take the cross product of this del operator with the vector field A. If you do that, that's called the curl, which is a vector function as well, since the cross product yields a vector. And these are basically three different ways to take first derivatives of three-dimensionally defined quantities. Whether your quantity is a scalar or a vector, you can take basically a spatial derivative. There are also a couple of second derivatives that we'll define. The second derivative for a scalar field is called the Laplacian. And that would be del squared v. And the definition of that is the second derivative of your scalar field with respect to x plus the second derivative of your field with respect to y plus the second derivative with respect to z. Right, and this is called the Laplacian. And it is also a scalar. All right. If you want to take the second derivative of a vector field, right, the grad squared of A, that's actually defined as the scalar Laplacian of each of the underlying elements of A, or the components of A. So in other words, it's the Laplacian, the scalar Laplacian of the x component of A in the x direction, plus the scalar Laplacian of the y component of A in the y direction, plus the same for z. All right, this is called the vector Laplacian. We're going to get to these later, so don't worry about these right now. For today, we're just going to concern ourselves with the divergence, which will be the grad operator applied to a vector, and it's going to yield us a scalar. But the rest, we're going to save for later. All right. So let's take a look at what divergence means. Right. So it's the del operator dotted with some vector A will be equal to the derivative of the x component of A with respect to x plus the derivative of the y component of A with respect to y plus the derivative of the z component of A with respect to z. All right. Remember, ax is a scalar because it is only the x component of this vector A. And we're taking the derivative of whatever is there with respect to x. And we're adding these up. So this is called the divergence. And the reason it's called the divergence is the following. It's basically going to measure, if I take a really small box in space, it's going to measure to what degree the field lines are emerging from or converging into this box. So for example, if I have a bunch of field lines that are all crashing into this very small box, that would be an example of a negative divergence. The opposite is true. If I have a really small box and I've got lots of field lines that are spewing out from this location, that would be an example of a positive divergence. So a positive divergence means a net outward flow of vector lines. An example of a zero divergence would be if I have a small box right here and all the field lines that kind of come into this box also cross through to the other side. So something like this, right? This would be the example of no divergence. All right. So let's just go back to our qualitative Gauss's law understanding of what Gauss's law mean. It basically is that the integral over some surface, we have some amorphous blob, right? It's a shape that has a volume inside of it. And in that little amorphous blob, we've got little vectors ds that point out, pointing away from the volume out of the shape. And if we walk around the surface of this entire object, and that's why we have a circle right here in this integral, and take the integral of the d at every location and dot it with the little surface vector, that's going to equal to the total charge that's inside the volume or inside of that shape, right? So it's the integral over the entire enclosed volume of the volume density integrated over the volume, right? So this right side is just the total charge within. So total charge within. And this left side is the total outward flux. All right, remember, D is flux density in units of coulombs per meter squared. So you multiply it by an area, and that's a total flux, not a flux density anymore. So that's what the left side of this is. All right, and this was basically a way to restate what we already knew, which is that field lines have to start at positive charges and they have to end at negative charges, right? Positive charges are sources and negative charges are sinks. And so this divergence is convenient because this is basically a measure of sourciness, right? If it's positive, then you've got a very sourcey location, right? Lots of field lines are popping out. If it's negative, then it's sort of like unsourcey because things are being sucked into it. It's like a drain. All right. So given this, we can probably directly relate the divergence of the electric flux density D is going to equal to something very close to the charge. And it turns out that Gauss's law can be reformulated in the following way, that the sourciness or the divergence of the electric flux density equals the volume charge density, right? This is volume charge density. In units of coulombs per meter cubed. And this is the sourciness of the electric flux lines. So in some sense, this kind of restates what we already knew, that positive charges act as sources of electric flux lines and negatives as sinks. It just restates it in a form that's only concentrated in a very, very small area, since this is differential. So this is Gauss's law in differential form. All right, so that is divergence, and that's how divergence immediately leads us to this notion of Gauss's law in a different form. All right, in the next video, we are going to look at basically how we can convert from one form to the other very briefly, and we're going to look at analytically how you might solve Gauss's law, even though oftentimes that's not going to be very useful in real life.